Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start chapter 7, which is system design, addressing design goals. So in the previous lecture we have discussed system design activities, that how we moved from objects to subsystems. So we started with the analysis model for a route planning system, which was MyTrip. So we identified design goals for MyTrip in keeping in mind the non-functional requirements. After that, we designed an initial subsystem decomposition for MyTrip. So now in this lecture we are going to discuss system design activities that basically refine the subsystem decomposition that we have done previously. So these activities involve hardware software mapping, data management, global resource handling, control flow, and software control and boundary conditions. So keeping in view the previous slide, we can say that the third activity is mapping subsystems to processors and components, or hardware software mapping. So there are two activities. This system design activities addresses two issues: selecting a hardware configuration and a platform, and second is allocating objects and subsystems to nodes. So first issue is selecting a hardware configuration and a platform. So hardware mapping activity has significant impact on performance and complexity of the system. So many system runs on multiple computers. So the use of multiple computers can address high performance needs and interconnect multiple distributed users. So the mapping activity, the hardware software mapping activity has significant performance impact. That's why we need to perform it early in the system design. So selecting a hardware configuration also includes selecting a virtual machine onto which the system should be built. So what is virtual machine? Virtual machine includes operating system and any software component that are needed by the system. So the figure below shows the hardware allocation for MyTrip. So in MyTrip, we from requirements we identified two subsystems, which are planning subsystem and routing subsystem. So they run on two different nodes. So routing, as we have already discussed this case study, you are already familiar that the routing subsystem will be on onboard computer. So this device indicates the node or the hardware. So but this planning subsystem is a web-based service, so on the internet host. So the MyTrip has two nodes. So allocation of MyTrip subsystems to devices and execution environment. As you are already familiar that which UML diagram shows the mapping between software and hardware, UML deployment diagram. So routing subsystem runs on onboard computer and planning subsystem runs on Apache server. So a node can be, you can represent a node inside another node as well. So allocating objects and subsystems to nodes. So once objects and subsystems are assigned to nodes, after this often triggers the identification of new objects and systems, because now these subsystems have to communicate with each other. So allocating subsystems to hardware nodes enable us to distribute the functionality and processing power across the nodes. So in the case study that we are discussing, MyTrip, there are two subsystems, routing subsystem and planning subsystem. So they share common objects. So they need to communicate with each other. So that's why we created a new subsystem to support this communication, so which we call communication subsystem. So communication subsystem is a subsystem that is located on both nodes, and both nodes are one for routing subsystem and one for planning subsystem. So communication subsystem located on both nodes and responsible for managing the communication between them. And why communication is required? Because they share common objects. So this is the revised design model for MyTrip after adding the communication subsystem into it. So this communication subsystem is responsible for transporting objects from planning subsystem to routing subsystem. This connection represents an active link between the planning subsystem and the routing subsystem, and the message represents a trip. It represents the information of the trip, its related destinations, its segments, its crossings, etc. Another example of hardware software mapping shown by UML deployment diagram of Arena case study. So this Arena has two types of nodes: the user machine, which provide a user interface, and a server machine to run the application logic and storage to provide the Arena services. So Arena client and match front end peer subsystems run on user machine, and these subsystems run on server machine. Two types of diagram we are using in this lecture. We have already discussed these diagrams. One is deployment diagram, which illustrates the distribution of components at runtime. So it uses nodes and connections to depict the physical resources in the system, and the component diagram which illustrates dependencies between components at design time, compilation and runtime. So you are already familiar with the notations of the deployment diagram. Component diagram, it is also called software wiring diagram. So next is data management. So some objects in the system model need to be persistent, and persistent data is the one whose value for their attributes have a long lifetime, longer than a single execution. For example, at the end of the day, an author saves his work into a file on a word processor. The file can then be reopened and used later. So, where and how data is stored has an effect on the decomposition of the subsystems or the system. So this is a subsystem decomposition of my trip after deciding on the issues of data storage represented by UML component diagram. So in my trip, it is decided to store the current trip information in a file. Fine, to store the current trip information in a file so that recovery of the current trip is possible in case the driver shuts off the car before reaching the final destination. But the trips information will be stored in the database. So using a database for this system allows to perform complex queries on the data. So trip file store subsystem, the trip file store subsystem is responsible for storing trips in files on the onboard computer on which routing subsystem resides. Because this functionality is only used for storing trips when the car shut down accidentally, this subsystem only supports the fast storage and loading of the whole trip. So we don't require database storage over here. But as the trip information will be stored in database, because this subsystem can be used to manage all trips for many or all drivers. So it need to be stored in database. So map, because here concurrent access is required because it is used by many drivers at the same time. So map database store subsystem is responsible for storing maps as well as trips in a database for the planning subsystem. The subsystem supports multiple concurrent drivers and planning agents. So as I have said in the previous slide that where and how data is stored affects system decomposition. So as you can see now, we have decided two strategies to store the data, and it has an effect on the system decomposition. That there is one subsystem for trip file store subsystem, and there is another subsystem for database storage. So identifying persistent objects. So persistent objects need to be identified first in order to store them. So entity objects identified during analysis are best candidates for persistency or to become persistent objects. So identify persistent objects by examining the classes that must survive system shutdown, whether system is closed accidentally, whether it is an unexpected crash or a controlled shutdown. The system will then restore these persistent objects by retrieving their attributes from the database even after the system shut down unexpectedly or in a controlled way. So persistent objects can be stored with one of the following mechanisms. So using flat files or file systems, or using database. Database can be relational or object oriented. So we use flat files or file system for huge volume of data. For example, if there are images in your data set, or if the data are used by multiple readers but a single writer, then this mechanism is this option is better. And database, this option is better if concurrent access by multiple users is required. So if there are multiple platforms or applications for the same data, so if data are used by concurrent writers and readers, then this storage management option is better. So next is providing access control. It includes discuss access control, describe access rights for different classes of actors, and describes how object guards against unauthorized or illegal access, thus providing security. So in a multi-user environment, different actors usually have different access rights to different functionality and data. For example, an everyday actor may only access the data it creates, while an administrator may have unlimited access to system data and to other users' data as well. So how do we model these accesses? During analysis, we model them by associating different use cases with different actors. And during system design, we model them determining which objects are shared among actors. So we model access on classes with an access matrix. In access matrix, the rows of the matrix represent the actors of the system, and the columns of the matrix represent classes whose access we want to control. And what is access right? It is an entry in the access matrix. It lists the operations that can be executed, like post, like examine, select. So it lists the operations that can be executed on instances of the class by the actor. I will show you with the help of an example of a bank teller of a banking system. So, access matrix for a banking system. So, a bank teller may post credits as well as debits and examine his balance, while a manager must approve the transaction. He can perform these operations. He can examine branch statistics but cannot access statistics of other branches or the whole corporation, while the analyst can access information across all branches of the corporation but cannot post transactions on individual accounts. So this access matrix defines the access right of each actor on the objects of the class. So this represents access right, like post small debit, post small credit, examine balance. This represents access right. So we can represent the access matrix using one of three different approaches. One is global access table. So it represents explicitly every cell in the matrix as a tuple. So actor, class and operation. Like this represents a tuple in the global access table. So league owner is an actor and this actor can view arena, and league owner is an actor and it creates a tournament. It can view the tournament as well. So this is an example of global access table, which represents explicitly every cell in the matrix as a tuple. So actor, class and operation, for which the actor is responsible for. So determining if an actor has access to a specific object requires looking up the corresponding tuple for that. So next access matrix representation is access control list. So association associates a list of actor, operation, pairs with each class to be accessed. Every time an instance of this class is accessed, the access list is checked for the corresponding actor and operation. An example of it is, for example, a butler checks the arriving guests by comparing their names against names on the guest list. If there is a match, the guest can enter, otherwise not. So another representation is capability. So it associates a class operation pair with an actor. So a capability allows an actor access to an object of the class described in the capability. So an example of it is an invitation card for a party. So in this case, the butler checks if the arriving guest holds an invitation card. If yes, if the invitation card is valid, the guest is allowed, otherwise not. So the representation of the access matrix has an effect on performance. Global access tables requires more space. Access control lists make it faster to answer the question that who has access to this object, whereas capability lists make it faster to answer the question which objects has this actor access to. So this is an access matrix example for arena case study. As you can see, the rows of the matrix represent the actors and the columns represents classes whose access we control. So arena operator is an actor and it can create user of the arena. It can deactivate. It can archive league. League owner is another actor and it can get status of the user, get status and information of the user. So this represents access right. Spectator is another actor and it can apply for player, apply for advertiser in arena. So an example of access control list in which the access control list for match M1 is provided, in which the actors access is given, that these actors may access or may not access. So जो player want to play the match and the gatekeeper checks against the access control list and decides whether the access should be allowed or not. So this is example of capability realization. Here the player Joe has the ticket for match M1 and gatekeeper just check the validity of the ticket. If the ticket is valid, the access will be allowed to the actor. So next is designing global control flow. So control flow is basically the sequence of actions in a system. So it is in object oriented systems, control flow is basically deciding which operations should be executed and in which order. So these decisions are based on external events. External events generated by some other system or some user. So these decisions are based on external events generated by an actor or on the passage of time. So basically there are three possible control flow mechanisms. One is procedural control, procedure driven control. second is event driven, and third is threads. So in procedure driven approach, operation wait for input whenever they need data from an actor. So in this approach, the operation requires input from the actor. And an example of procedure driven control, the code prints out message like this, it print out message and waits for input for the user, and next it is waiting for input from the user to perform the security check on the input provided by user. Next is event driven control. In this, a main loop waits for external event. So in event programming, there is generally a main loop that listens an event and triggers a function as a result of that event. So whenever an event becomes available, it is dispatched to the appropriate object based on information associated with that event. So generally there is one loop that is responsible to listen an event. So that is basically it is centralizing all input in the main loop. Like an example of main loop for event driven control, an event is taken from an event stream. An event is taken, event stream dot has next, and sent to objects interested in it, and then sent to objects interested in which perform further processing on event. So in this case, control flow is driven as a result of event. So once a control flow mechanism is selected, that whether it is event based or thread based, then it is recognized with one or more control objects. So the role of control objects is to record external event, store temporary states about them, store the state of the event, and issue the right sequence of operation calls, that what will be the order of the operations on the boundary and entity objects associated with that external event. So after selection of control flow mechanism, these sequence of actions will be executed. So control object will record external event, save its state, and issue the right sequence of operations on boundary and entity objects that are associated with that external event. So till now we have discussed that how to decompose the system, how to distribute use cases among the subsystems, how to store persistent data, how to identify persistent data, how to achieve access control, and how to design global control flow. Now we need to examine the boundary conditions of the system. So boundary condition is what? Boundary condition will decide how the system is initialized, shut down, and how it is started, and how it deal with major failures such as data corruption, bugs, errors, how the system will deal with it. So use cases that deals with these conditions, with initialization, with termination, with failure, the use cases which deal with these conditions are called boundary use cases. So boundary condition questions, that what questions need to be addressed while designing the boundary use cases. So initialization, what data need to be accessed at startup time, that when the system is starting, what data should be accessed by the system, what services have to be registered on the system while the system is in startup stage, and what does the user interface do at startup time. In the same way, termination, are single subsystems allowed to terminate without the termination of the main system, and are subsystem notified if a single subsystem terminates. So these questions need to be addressed. And failure, how does the system behave when a node or a communication link fails, and how does the system recover from failure. In general, this deals with major failures such as data corruption and network outage. So boundary conditions are best models as use cases, which we call boundary use cases with actors and objects. We call them boundary use cases or administrative use cases. Actor, in which actor is often the system administrator, and because these use cases deal with initialization, termination and error related conditions, so the use cases can be startup of system, subsystem, startup of full system, termination of subsystem, and error in a subsystem or component. In the example that we are discussing for my trip, a new use case is added to cover boundary condition, that is manage server, and it includes start server, shutdown server and configure server to cover the boundary conditions. Actor of this use case is server administrator. So the description of start server boundary use case is given in next slide. So start server is basically part of manage server. So by adding the use cases in the existing my trip use case model, it has no effect on subsystem decomposition, like no new subsystem is added to handle these use cases. Rather, existing subsystem, that is map db store subsystem, should be able to detect whether or not it was properly shut down and should be able to perform checks. So as a result of adding these use cases, the description of map db store subsystem is revised and no new subsystem is added. So this is the description of start server use case that covers the boundary condition for startup the system. So the planning server administrator should be login to the server is the entry condition for this use case, and flow of events for this use case are given, and then exit condition is mentioned that the planning service is available and waits for connection from routing assistant, that is your other subsystem. So as a result of, as I told in the previous slide, that as a result of adding these boundary use cases, the description of several the description of existing subsystems may be changed, like when the managed server is added to handle the boundary condition, as a result of which map db store subsystem description is revised, and these the text in italics show the revised description of map db store subsystem. So when starting up, the map db store subsystem detects if it was properly shut down, and if it is not shut down properly, it performs a consistent check on maps and trips and repairs corrupted data from the previous run if necessary. So this is the revised description for map db store subsystem based on the additional start server use case. So changes are indicated in italics. So in this lecture we have discussed system design activities, that basically how to refine the subsystem decomposition. What are the activities involved? So these are mapping subsystems to processors and components, then how to store persistent data, then how to provide access control, then how the control flow, selecting the control flow mechanism, and then identifying the boundary conditions, and as a result of identification of new boundary use cases, revising the subsystems description. So each of these activities may affect the subsystem decomposition. Maybe as a result of these activities, new subsystems may be added, or the description of certain subsystems may be changed. So two UML diagrams we used in this lecture to represent these activities, that is UML component diagram and deployment diagram. The notations of these diagrams, you are already familiar with the notation of these diagrams. So that is all for today's lecture. Thank you.